So in this chapter, we'll focus on the growth of functions and the complexity of algorithm. Okay, we compare algorithm depending on the number of basic operation, and if you have two algorithm solving the same problem, which algorithm is more faster and converge its runtime is less than we compare runtimes, okay, in some way. So for the growth of a function, we'll define big O notation, big omega notation, and big theta notation, okay? We'll understand this asymptotic behavior, we say, when the size of your problem is become large, okay? You know that now the trend is to deal with big data, okay? So this is a very important question when you choose an algorithm to solve your problem. So time and is very important, memory as well, okay? So it's important to understand how quickly we can solve a problem at the size of the inputs grows, okay? By comparing the efficiency of a different algorithm for saving the same problem and choosing the best one. Okay, let's start with the big O notation, which give us an upper bound of a function as x becomes large, okay? So this is the definition. We say that a function f of x is a big O of another function g of x as x is large, so greater than a given value k, where f of x is less than a constant times g of x. So we interest for x for large value of x. We say the asymptotic behavior of our function. Okay, so this says that f blows up or grows no faster than the function g. Okay. The constant c and k here are called the witnesses of the relationship, and they are not unique. Okay, these constants are not unique, but it gives us the behavior of the function asymptotically. Okay, for large values of x. Okay, this is an example of a polynomial function of degree n. Okay, so if your function is polynomial with degree n, these are the coefficients, then we can say that a polynomial function is big O of x power n. Okay, the polynomial function is big O of xn. This means that all these terms can be neglected compared to xn. When x is large, xn dominate the other terms. Okay, مثلا إذا x 10 و n 5 مثلا. Okay, so x is 10, x square is 100. Okay, it's much larger than x. X cube is 1000. Okay, so we can neglect the terms, the quadratic terms with respect to cubic terms. Okay, so the leading term give us the speed of a blow up of our function. The reason, okay, we can say that fx, the absolute value of fx, this is the expression of fx, okay? And we know that the absolute value of the sum is less than or equal the sum of absolute values. Okay, so we can say that this quantity is less than an xn plus an minus 1 xn minus 1 plus a1 x plus a0. Okay, and here we see that we know that xn minus 1 is less than xn. For example, when x is greater than 1, we know that xn minus 1 is less than xn. That xn minus 2 is less than xn. That x is less than xn. That the cons xn is greater than 1. Okay, so we can make xn as a common factor. an plus an minus 1 plus a1 a0. And this will be our constant c independent of x. And we see that this polynomial function of degree n with leading coefficient non-zero, so it's really degree n, is less than c x n. So we can say that f of x is a big O of xn. Okay, so asymptotically, this function, this polynomial, grows, okay, asymptotically, or converge asymptotically, no faster than xn. This is the idea. So here again, the leading term, this term, okay, dominates the growth of polynomial function of degree n when x is large. So for example, if we have the sum of the first n positive integers, n plus 2 plus till n, okay, here again, we can say that 1 is less than n, 2 is less than n, all terms are less than n. So we can have this upper bound, the sum of n. How many times? Here we have n items, n terms. Okay, so n plus n plus n, n times, it's n times n. So it's n squared. So we can say that the sum of the first n positive integers, this is a big O of n squared. Okay, it asymptotically, it converges no faster than n squared. So these are some behavior, asymptotic behavior of some known functions. What's the big O of the factorial function? So we know that the factorial function is the product of the integers from 1 to n. Okay, so here again, we can say that each term is less than n. Again, how many terms? We have n terms. Then n phi n phi n times is n to the power n. Okay, so we can say that the factorial n is a big O of n to the power n. So for log n factorial, the same. So we know that we have seen that n factorial is dominated by n to the power n. If we apply the log, log is an increasing function. So log n factorial is less than log n to the power n, and we know the properties of log. Log x to the power a ممكن نطلع A برا تصير لي A log X. So we can do the same here and we obtain N log N, and we can say that log N factorial is the big O of N log N. So this is the behavior of log N factorial when N is large. Okay? And this is very important. So this gives us a comparison of the behavior of function as n gets larger. Okay? So we see that for a constant function, so it's a constant. Here log n blows up faster than constant, but still slow blow up. Then n blows up faster than log n log n faster than n and faster than log n, and then any powers of n, okay, n square, n cube. So when n is 8, we'll need, okay, for example, this is time complexity, or this is number of iteration. So the number of iteration grows fastly. So here n factorial blows up faster than powers of n, than exponential values. Okay, this means that the complexity, the time complexity here is very high. Okay, if this is related to the number of operation, okay, if your algorithm make n basic operation is faster than an algorithm which needs n square basic operation. Okay, basic operations is faster than an algorithm which needs n square operations. Okay, we can say that this is somehow related to the number operation, and as the number of operations grows, okay, your time complexity is higher. Okay, so regarding the number of operation, okay, time complexity, so an algorithm needing log n operation is faster than an algorithm which needs n square operation. Okay, so this is very important when you have to choose an algorithm given a problem, and to compare algorithm. If you have several choices, of course you choose the faster لأنه very important. ممكن تفرق معاك algorithm يعطيك the result in seconds or in minutes, والآخر يعطيك in days or in month. Okay, so it's not just that the algorithm converge, give you the result, but the time is very important. Some properties. So if F1 is a big O of G1 and F2 is a big O of G2, then F1 plus F2 is a big O of the max of G1 and G2. What does it mean? It means that if you have your function F1, for example, is a big O of x cube, your function F2 is a big O of log x. Okay, so the sum F1 plus F2 will be big O of the max of x cube and log x. ومين أكبر x cube or log x؟ قلنا الأكبر هو x cube when x is large. Okay, so here the sum is a big O of x cube, since x cube blows up faster than log x, dominates log x. Okay, x cube dominates log x. Okay, so the behavior will be given by x cube here. If both they have the same behavior, they are both big O of g of x, so the sum will be big O of g of x, since here the max of g and g is g. For the product, it's a big O of g1, g2. Okay? So كما قلنا if f1 is a big O of x cube and f2 is a big O of log x. So the product f1, f2 will be a big O of x cube log x. Okay, this is the asymptotic behavior of this function as x becomes large. And as I said, this is related to the complexity of the algorithm. Okay, this is to decide how efficient is your algorithm for solving a given problem for a particular size of input data. Okay, and now the input data are large sets, very large sets. Okay, so this is very, very important. So how much time and how much computer memory? I don't know which type of algorithm did you use so far, but personally, I faced several times, okay, getting when running an algorithm, getting an answer that so the algorithm crashes and I get out of memory. Okay, out of memory message. So my computer is not able to run this algorithm because it needs more memory than what is available. Okay, so you can face this problem. I don't know whether you did yet or not, but you will face this problem. So this is also important. So the complexity of an algorithm is a function of n, which is related to the number of operation, okay, given the running time or the storage space requirement of the algorithm, depending on the size of your data. So space complexity usually is a big O of n, but time complexity is, as we have seen, is a bit more complicated. It depends on the size of the data, but it depends on your data as well. Okay. So this is an example. We want to search, we have a short text. هذا الكل نسويه عندنا word text ولا PDF, and we look for a given word. Okay, so we search for this word. Okay, so هنا يقول لك إذا الword متاعك the, okay, it's more likely that you find it quickly because we use lot of we use the several times in a text, so the first occurrence will be at the beginning of the text. Okay, so FN will be small, the first occurrence. Whereas if you use the word zoo, okay, this is not used frequently, so it might appear at the end of the text or it might not appear at all. So here Fn will be large compared to the first search. Okay, so here your computer will need much more time to find zoo compared to the word the. Okay, this is an easy term, so the difference is a fraction of seconds. Okay, but for large data, okay, this is, of course, this will be a very important parameter to take into account when you choose your algorithm. So as I said, the complexity, the time complexity is related to the number operation, how many addition, how many multiplication, how many division we do, and this give us, okay, in order big O or a big theta of the number of operation and give us information about the speed of convergence of your algorithm. For example, a well-known algorithm, the linear search algorithm, okay, as I told you, if you want to search for a given word, okay, so to locate an item X in a list of K items N1 to Nk, okay, by examining the list one at a time, starting at the beginning. So the idea is to compare X with N1. If you find the item you are looking for, you stop you are done. Okay, you find your item. If X is different from N1, you compare with the second element. If you are okay, so you are done. If not, you continue and so on. Okay, till comparing X to all items. Okay, so at the worst case, okay, you compare it to the last one nk. يا إما هو يا إما it returns zero, which means that your item is not an element of this list. Okay, this is called the linear search algorithm. Okay, and the complexity here is the number of comparison between an item and an element in the list. Okay, so here the time complexity, okay, the worst case is ck. Okay, the worst case is you do k comparison. Okay, this is the worst case, it's k, you make k comparison. The average case, it depends on the probability that your item is at a given position k. Okay, so here we assume that it's likely equal. Okay, it can be at any position with the same probability 1 over k. Okay, so here this is the complexity, okay, depending on the size of your list. Since we assume that it has the same probability to be at any position, so we can make 1 over q as a common factor. The sum of the first k integers, this is known, we'll study it in chapter 6. It's k plus 1 over 2 over 1 over k. So this is the time complexity, k plus 1 over 2. So half time, okay? The average case compared to k, the worst case, okay? So these are key elements to consider prior to run your algorithm. Okay, before you run your algorithm, it's important to have an idea about time complexity and storage complexity. لأنه بعض الأحيان you choose an algorithm and it needs days and weeks to convert to give you the expected output. So this is a quick
Yes.
description of time complexity on behavior of a function when the size of input becomes large.